Hello everybody, welcome to the week 3 lesson of our cryptography course. As we saw at the previous lesson, the main weakness of monoalphabetic substitution ciphers is that each letter in the ciphertext corresponds to only one letter in the plain text. It makes cryptanalysis of this type of ciphers very easy. Therefore, people invented some stronger ciphers. The idea for a stronger cipher where it would be possible to hide the language features was by Albertini in 1416. To hide the distribution of letters in a language, it was necessary to invent a cipher in which one letter of an alphabet could be encrypted into different letters within one plain text and with one key. This type of cryptosystems in which multiple substitution alphabets are used are called polyalphabetic ciphers. Each alphabetic character of the plaintext can be mapped onto n alphabetic characters of ciphertext, and usually this n depends on the encryption key. In our course, we are going to consider Vigenère cipher, the autoclave cipher, and the Hill cipher. Also, we are going to study permutation ciphers. However, the encryption principle behind this type of cryptosystems differ. Let us talk about everything in order. So, we start with Vigenère cipher. The best known example of polyalphabetic ciphers is the Vigenère cipher, which was invented in 1586. Again, we assume that the language of encryption is English, so our plaintext space and ciphertext space are limited to 26 letters of English alphabet. However, we say that one letter of a plaintext can be mapped onto different letters of a ciphertext depending on the position of this letter in the text that we are encrypting. Suppose that there are n letters in our plaintext, so accordingly there will be n letters in our ciphertext as well. Then we define the set of plaintext and ciphertext as set of integers modulo 26 letters, since there are 26 letters in our alphabet, to the power of n, since we apply n permutation of these 26 letters. In addition, in polyalphabetic ciphers, a cipher key will be defined by a sequence of letters. So recall that in monoalphabetic ciphers, we use just one number that could define our encryption key. So suppose that the length of the key sequence is m. Then we define our key as a sequence of k characters. Now we can define the encryption algorithm and the decryption algorithm. As we can see from the encryption and decryption algorithms, this algorithm is similar to the shift cipher, but unlike shift ciphers, it encrypts and decrypts m letters in a block each time. Again, it's easy to see that if we decrypt the ciphertext, then we again obtain the plaintext. So let's consider everything on an example. Suppose that our plaintext is the word cryptography. According to our algorithm, we can choose the key as some combination of letters. For ease of remembering, let us choose as a key some meaningful word. So our key is going to be the word luck. The length of word cryptography is 12 letters, while the length of word luck is 4. So our n is equal to 12 and m is equal to 4. Recall that n is the length of plaintext and m is the length of keyword. To encrypt a message which is longer than cipher key, we can reuse the key. Thus, for every letter of plaintext pi, where I is more than m, and this I defines the position of letter in the text, we use the repetition of cipher key as p m plus I plus ci. That is, for example, here we have the position of letter t equal 5. 5 is more than the length of our keyword. So to encrypt this letter t, we use the first letter of our keyword again. That is, its position is m plus 1 and its position is 1. Also, recall that we encode every letter of an alphabet with a number from 0 to 25, so that A becomes 0, B becomes 1, C becomes 2, and so on up to Z, which is encoded as 25. After encryption, we obtain the ciphertext, which starts with M, L, A, Z, E, and so on. If we look at our ciphertext carefully, we can see that the letter R at the second position was encrypted as L, and letter R at 8th position was encrypted as B. Same can be said about the letter P at the 4th position, which was encrypted as Z, and letter P at 10th position was encrypted as J. Thus, the language features are not preserved, which makes the use of frequency analysis more difficult in case of polyalphabetic ciphers. Let us consider another way to encrypt the message without encoding letters to numbers. For that, we can use so-called Vigenère square. This is a 26 by 26 table with A to Z at the heading row and at the first column. Starting with the second row, each row has a letter shifted to left by one position in a cyclic way. As you can see, B shifted to the left, so did C, and A is at the last position at the second row, and so on. Or at the last row, we see Z at the first position. To encrypt a letter of the plain text, we pick this letter in the first column. That is, we use it as a row index. Next, we pick a corresponding letter of key sequence. So, in our case, our first letter of plain text was C for cryptography and L of luck. The entry at the row column intersection is our letter of the ciphertext. So this is the easier way to encrypt a message using Vigenère cipher. So if we talk about the key space in Vigenère cipher, if the length of our keyword is denoted by M, then there are totally 26 to power M possible key sequences. For example, if N is equal to 5, then the key space is equal to 26 to power 5, which is a large enough number to prevent exhaustive key search attack. Let's consider the cryptanalysis of Vigenère cipher. Vigenère cipher masks the frequency with which a character appears in a language. One letter in a ciphertext corresponds to multiple letters in a plain text. It makes use of frequency analysis more difficult, but yet it is possible. So let us see how we can apply the frequency count to the cryptanalysis of Vigenère cipher. For that, we can consider any message encrypted by a Vigenère cipher as a collection of many shift ciphers. The number of shift ciphers is as many as there are letters in the key sequence. So the problem of breaking the cipher reduces to problem of finding the length of the key. So for example, we had the word cryptography in our previous example, which was encrypted using the word luck as a key. To apply a frequency count, we need to find every letter that was encrypted using the letter L, for example. So we are considering the collection of these letters, and we calculate the frequency of each letter in the first column. Next, we calculate the frequency of letters on the second column to determine every single letter of our key. In our case, we would solve 4 shift ciphers at each of column. Of course, with our example, we will not be able to solve it since our ciphertext is too short. For Vigenère cipher, as the length of the keyword increases, the letter frequency shows less English or French or any language like characteristics and becomes more random. When the key length m tends to infinity, we can call this type of cryptosystems as one-time path, but we will study this type of cryptosystems later on. So, we said the problem of breaking a cipher reduces to the problem of determining the key length. There are two methods to find the key length, which are Kosinski test and index of coincidence. Let us try to find the key length using Kosinski test. In this test, we exploit the fact that two identical segments of plain text will be encrypted into the same ciphertext if they occur in the text at some distance delta. So for this distance delta, we assume that if we take delta modulo the length of the key, that it would give us 0. That is, in Kosinski test, we look at repeated sequences of 3 and more characters, and we can define the search algorithm as follows. We search for pairs of identical segments of length at least 3 characters, and we record distances between two identical segments, delta 1, delta 2, and so on. And we assume that the length of the key divides the greatest common divisor of distances between these segments. Let us consider the Kosinski test on the example. So, suppose we have the ciphertext of this form. We can observe that the substring CHR occurs 4 times in our ciphertext, and this CHR occurs at positions 1, 21, 41, and 66. So we calculate the greatest common divisor of distances between these positions, which is equal to 5. So we expect the keyword length to be 5. We can write this ciphertext as a collection of 5 ciphertexts and apply a frequency analysis to each of these blocks. So from this column, we try to deduce the first letter of our key. From this column, we will try to deduce the second letter of our key sequence, and so on. As we saw, if we define the length of our plaintext, then applying frequency analysis to each column separately, we can deduce the keyword. The second method is so-called index of coincidence method. In this method, we measure how similar a frequency distribution is to the uniform distribution. But we know that in the natural language, the distribution of letters cannot be uniform. Some letters occur more often than others. So all of the probabilities, that is, probabilities of all letters in the alphabet, must add to 1, and the index of coincidence of a ciphertext does not change if the text is encrypted with a substitution cipher. So we try to get the index of coincidence close to those of English language. So for that, let Fi be the number of occurrences of the ith letter of ciphertext, and let L be the length of keyword which we are trying to guess, and let N be the length of ciphertext. Then we can calculate index of coincidence by this formula. Let us show where this formula comes from. Suppose that we have a language where all 26 letters are used with the same frequency. Then the probability that we pick a letter A is equal to 1 over 26. I think it is quite clear. So if we try to pick 2 letters A from the set of alphabets, then we would have 1 over 26 multiplied by 1 over 26. That is, from one alphabet we have one chance out of 26 that we pick the letter A, and from second alphabet we again have one chance out of 26 that we pick the letter A. So probability that we pick two letters A is the multiplication of these probabilities. If we calculate the probability of pulling out two random letters, then this probability would be out of 26 we are trying to choose two random letters. So these 26 are cancelled and we have 0.0385. If the distribution of our letters were uniform, the index of coincidence would be this number. However, this distribution is not uniform. As we said before, some letters such that E occur more often, while others, for example Z, occur less often. The index of coincidence is the probability that two random elements of a ciphertext are identical if we denote the frequencies of letters A, B, C, so on up to Z in some text which we denote by X, and our X is the sequence of letters. If we denote these frequencies of occurrences of letter A, for example, by F1, the frequency of B in the ciphertext by F2, and so on, we can choose two elements of X in N chooses two ways. I think you remember this notation from combinatorics lesson. Recall that N choose K, for example, is calculated as n factorial divided by n factorial multiplied by n minus k factorial. There are Fi chooses two ways of choosing two same elements because, as we said, this Fi is the frequency with which this letter occurs. Hence, we have this formula. Index of coincidence of a string written in English is approximately equal to 0.065. The same reasoning applies if X is a ciphertext string obtained using a monoalphabetic cipher. Moreover, by calculating the index of coincidence, we can find out what cipher was used to encrypt a given ciphertext. It's not just a way of determining the key length. If the index of coincidence is close to this number for a ciphertext encrypted in English language, then the language features were preserved. That means that this message was encrypted using one of monoalphabetic ciphers. Let us continue with our example. First, let's assume that the length of key sequence is 1. Then we just rewrite our message and calculate the occurrence of each letter. Thus, in our ciphertext, A occurred 3 times, B occurred 3 times, and so on. We have the distribution table written over here, and there are 66 letters in the plain text. So if we calculate the index of coincidence, we have for the letter A, we say there were 3 occurrences. So 3 occurrences multiplied by 3 minus 1 out of 66 letters in our plain text. So in the formula we see the summation sign here. So the next ratio is occurrence of the letter B. As we said, B occurred 3 times again, C occurred 4 times. Here we have 4, and so on. Calculating it for every single letter in the alphabet, we sum up these probabilities to 0.05035. This number is not close to 0.065. We can deduce that the length of our keyword is not 1. So we can assume that the length of keyword sequence is 2. We rewrite this our ciphertext, dividing it into 2 columns: C, H, R, G, Q, P, and so on. At the next step, we calculate the frequency of occurrence of each letter at the first row. For this row, if we calculate the index of coincidence, we obtain the number 0.0587, and for the second column, we obtain approximately the same index of coincidence. So this number is also not that close to index of coincidence of the English alphabet. So we continue assuming that the length of keyword is 3, 4, and we know that in our example the length of keyword is 5. So we can continue this way, and as we see, as the number of columns tend to 5, the index of coincidence approaches those of the English language, that is 0.065. In our example, when divided to 5, for the first column we are going to have index of coincidence of 0.08. This is because of the short length of our ciphertext, but with the text which is long enough we can achieve the big accuracy. On the other hand, if M is not the key word length, the string CI would look much more random. A completely random string would have, as we said before, the index of coincidence close to this number. If we suppose that n is very big, that is the length of our ciphertext which we were able to intercept is very big, then we can further approximate this formula, and this formula, if we put the real probabilities of occurrences of each letter of English alphabet, will give us the real frequencies of letters in English language, which was estimated as follows. And the index of coincidence for English language is 0.065, as we said before. Another cipher with the same logic is so-called keyword Caesar crypto system, where the keyword is used as a key, but after the keyword, as you remember, we rewrite this keyword in Visioneer cipher. In this crypto system, the rest of alphabet letters are used as a key and repeats are removed. So, for example, C was used here, so in the rest of alphabet C is removed, and so on. So letters which are already used in a key are removed. However, as we can see from the key generation, each key sequence length is predefined here. Since we are limited to 26 letters of the alphabet, then we know that our key length is 26, since after the keyword we use the rest of alphabet letters and repeated letters are removed from the key. Thus, if a ciphertext is long enough, we can use the frequency count, dividing a ciphertext into 26 ciphertext, and we can apply the frequency count to each of these 26 ciphertexts. If the ciphertext is short, we can just apply an ordinary frequency count with high probability of success. Thus, we can make the frequency count or analyze the text. So let's consider another example. Suppose that we are trying to decrypt this cryptotext encrypted using the keyword Caesar alphabet. We can make use of frequency count, or we can just try to analyze the text. If we have a closer look to our ciphertext, it contains two one-letter words. Here we have T and two Q's. So we can deduce that this must be A and I letters. Since T occurs once and Q occurs 3 times, it is likely that T is decrypted as I and Q is decrypted as an article A. The 3-letter word UPS occurs 7 times in the whole plain text. So with a high probability, this sequence is likely to be article the. So we can try to decrypt the remaining letters using high frequency groups. We can guess the remaining words. So as we can see, generation of the key sequence is very important, and in a sample of keyword Caesar crypto system we saw that by trying to add some diversity to the key sequence, we made our key weaker. Although the idea behind keyword Caesar crypto system was good enough, breaking the cipher a really easy task. Let us consider other method to generate some stronger key sequence. The next cipher we are going to study is an autoclave cipher. Again, we will consider this cipher on the example of English language, and our plaintext space and ciphertext space are limited to 26 letters of this alphabet. Autoclave crypto system is also a polyalphabetic cipher, thus supposing that there are n letters in our ciphertext and plaintext, we define the set of plaintext and ciphertext as a set of integers modulo 26, since there are 26 letters in the alphabet to the power n, since we can apply n permutations of these 26 letters. In addition, as we said before, in polyalphabetic crypto systems, our key is defined by a sequence of letters, and suppose that the key length is equal to m. So we define encryption algorithm and decryption algorithm. As we can see from these expressions, the encryption and decryption algorithms for the first m letters are similar to those of Vigenère cipher. However, after the first m letters are encrypted using the key sequence, to encrypt the m plus first letter of our plaintext, we use the first letter of plaintext itself. To encrypt m plus second letter of the plaintext, we are going to use the second letter of the plaintext, and so on. That is, after the first m letters encrypted, we start using the plaintext itself for sequencing the key. Let us see how the cipher works on an example. Suppose that we are encrypting this text using the keyword Hamburg. If we were working with Vigenère cipher, we would repeat the keyword as many times as needed to encrypt the whole plaintext. But in autoclave crypto systems, after using the keyword once, we started using the plaintext itself as a key. As we can see, first 7 letters are encrypted into the same ciphertext, but starting with the 8th letter at the plaintext, the encrypted versions are totally different because the keys are different. At autoclave cipher, after the keyword, the plaintext itself was used as a key, and since in the key there is no repetition, it is impossible to guess the key length, and this in its own turn makes frequency cryptanalysis impossible. So we can conclude that the security properties of this cipher are higher than those of Vigenère cipher. By choosing carefully the key sequence, we can make our crypto systems stronger, as is so at the example of Caesar keyword crypto system and autoclave crypto system. We should be very careful when generating the key sequence for polyalphabetic ciphers. Next cipher we are going to study is so-called Hill cipher, and it uses a bit of different technique for encryption. To be precise, the Hill cipher makes use of the linear algebra and modular arithmetic areas of mathematics. To understand how this cipher works, we need knowledge of matrix multiplication, modular inverses, determinant of matrices, and matrix adjugates, which are used for finding inverse. Let us define encryption and decryption algorithms. So let m be a positive integer. In our case, we take m to be equal to 2. This m defines the length of key, so if the length of our key is equal to m, we can apply m permutations. So our plain text and ciphertext spaces are integers modulo 26 to power m. As we saw in the Vigenère cipher, in polyalphabetic ciphers, a cipher key is defined by a sequence of letters. In our case of Hill cipher, we define a key as a matrix of dimension m by m. So here is our key matrix. All operations are performed in the set of integers modulo 26. For each key, we can define encryption algorithm and decryption algorithm. So let us consider this cipher in more detailed example. So as I said before, the key here is a matrix. Let key be defined as this matrix. We are going to encrypt the message attack at dawn. Since our key matrix is 3 by 3, we need to divide our message into blocks of 3 letters. So at each encryption, we encrypt 3 letters. So first 3 letters of our plain text are A, T, T, which are encoded to 0, 19, 19 respectively. To get our ciphertext, we perform the matrix multiplication. We take the key and multiply it by vector defined by our plain text. After performing the ordinary matrix by vector multiplication, we take modulo 26 of obtained numbers. Encoding gives us that these 15, 5 and 14 obtained after encryption are letter P, F, or. Encryption is just a multiplication of key matrix by a vector where we keep the encodings of our plain text. So let us consider how do we decrypt the ciphertext. To decrypt, we need to perform an inverse operation. That is, we need to multiply the ciphertext by inverse matrix of the key, and we do all operations modulo 26. At the end, we should obtain the plain text again. So here we need a matrix inverse operation. To calculate an inverse operation, we need to perform the following operations. First, we need to find the determinant of key matrix. Then we need to transpose the key matrix. For transposed version of key matrix, we need to find minors and find cofactors. Let us first define the term determinants of a matrix. Determinant of a matrix A, denoted by that A, is a complex number that can be calculated recursively. So if the size of our matrix is 1 by 1, then the determinant of a matrix is equal to the element of the matrix itself. If A is a matrix of size m by m, where m is greater than or equal to 1, we can calculate the determinant recursively by taking submatrices of this matrix. For example, if the size of matrix is 2, then determinant is defined by this formula. If 3, then determinant is defined by this formula, and so on. As the size of matrix increases, the complexity of calculating the determinant is also increasing. So in our case, we have 3 by 3 matrix, so we can easily calculate the determinant, which is 489. Taking the modulo 26 gives us 21. So we are done with calculating determinant. Next operation is matrix transposition, which is simply rewriting the rows of original matrix as the columns of the new matrix. So each row is rewritten as a column. To calculate the matrix of minors, for each element we ignore the values on the same row and column and calculate the determinant of the remaining values. For example, if we are calculating the element A11 here, we ignore elements at the same row and at the same column. For the rest of the matrix, we calculate its determinant. So we have minus 3 mod 26, which modulo 26 is equal to 23. But for now, we are going to use this minus 3 notation. And we do the same for every single element. For example, to calculate this 56, we ignored this row and this column and calculated determinant for matrix which consists of 4, 5, 17 and 7. So 5 by 17 minus 4 by 7 gives us 57 and so on. Next, finding matrix of cofactors means just putting plus or minus sign according to this rule. So if we add plus or minus sign, we obtain this matrix. And now, calculating the value of these numbers modulo 26, we obtain this matrix of cofactors. Finally, we multiplied obtained matrix of cofactors with the inverse of determinant. So we have calculated the determinant of the key matrix and it was equal to 21. The inverse of 21 modulo 26 is equal to 5, since 5 multiplied by 21 gives us 1 modulo 26. So, as a final step to obtain the inverse matrix, we multiply this matrix of cofactors with the inverse of the determinant. So, we have calculated the inverse key matrix. Now, we can decrypt our message. In our example, our ciphertext was equal to 15, 5, 14. By multiplying this ciphertext by inverse matrix which we have just calculated, we can decrypt the message, which was equal to ATT. We can encrypt and decrypt the rest of our plain text in the same manner. How can we attack a Hill cipher? The Hill cipher can be attacked using a non-plain text attack. Suppose that we were able to intercept m distinct plaintext ciphertext pairs with a key dimension m. Here is our intercepted plaintexts and here are our intercepted ciphertext. We can rewrite these plaintext ciphertext pairs as m by m matrices. After rewriting, we know by encryption algorithm that plaintext multiplied by key gives us the ciphertext. So we can use this fact to find the key, which is equal to inverse of plaintext multiplied by ciphertext. Here, inverse of plaintext means that if we multiply this inverse by the plaintext itself in set of integers modulo 26, we will obtain the identity matrix. It was a cryptanalysis of Hill cipher.